Hi, this is Theo, and this is the falling ball problem. Okay, so here's the situation. You've got a ball, there's an electromagnet that's kind of holding it up, and at a certain point we turn off the electromagnet, start a timer, and see how much time it takes for the ball to fall on this pad, and the height, or the distance from the ball to the pad is h. Okay, so first we were asked to find, oh yeah, and they're using this data to calculate the g, the gravitational constant. So, for part A, the experimenters noticed that the ball is actually released from the electromagnet a little bit after the timer begins, and so we're trying to find how that will affect the calculated value for g. So first, let's just find g in terms of h and t, and see if that can help us. So, using kinematics equations, we're going to define the positive y-axis as downward just because they're using that later. So in that case, if we set our href equals 0 up here, our initial height is 0, our final height is h, our initial velocity is 0, the ball starts at rest, and then we've got a plus 1/2 at squared, and in this case, oh, whoops, sorry, I forgot y is negative. Our final height is actually h, because we're starting from 0 and we're going down h. So h equals 0 plus 1/2 at squared. In this case, again, because y is positive as it's going down, if acceleration is related to gravity, acceleration is actually positive gravity. So h equals 1/2 gt squared, and then just solving for g equals 2h over t squared. That's our formula for g. Okay, so if the ball is released after the timer begins, what does that mean? Well, the height that it drops is still the same, but the measured time is actually going to be greater. So, I don't know how to write that, but the estimated time is greater than the actual time, and so g is proportional to the inverse of t squared. Then as t increases, the value for gravity is going to decrease. Therefore, the estimated value for gravity is going to be decreased compared to if the release was exactly when the timer began. So that's it. Okay, so next we're given some actual experimental data. It's up here. We've got the height in meters and the time in seconds. And we're going to try to use this to calculate g. So we need to define our horizontal and vertical axes such that we can kind of get a linear graph. So we know that g is equal to 2h over t squared. We can kind of rewrite that. Looks about the same, but just to make it clear that if h and t are our variables, our slope is going to be h over t squared, which means that h equals vertical. In other words, h is going to be the y variable, and t squared is going to be the x variable. So now that we have that, we're going to calculate t squared, because we already have h, but we need to find t squared. So let me get my calculator. Oh, I'm sorry. If that's the case. Okay, so 1.05. Oh, sorry, not 0.105. 0.213. Point 342. 0.401 squared. And 0.451 squared. And these are all in seconds squared. Okay, so that is basically part B. And then in part C, we are asked to actually graph this. So we're going to be graphing height versus time squared. I'll do my best on this, but it might be difficult. I also did it on paper beforehand so I can find a more precise slope. Okay. Okay, so our x-axis is t squared. In units of seconds squared. And our y-axis is h in units of meters. That makes sense because our units of gravity will be meters per second squared. Okay, so our t is going to range from about 0 to 0.2. Call that 0, call that 0.2. That's about 0.1, 0.15, 0.05. And then our height is going to range from about 0 to 1. This 1, 0.5, 0.7. Okay, and then we'll graph guesstimates for these points. Okay, so our first point is about 0.01, 0.1, so 0.01, could get that from there, and then we've got 0.045 about to 0.2. We've got 0.117 to 0.6. We've got it there. You've got 0.161 to 0.8. And we've got 0.203 to 1. So this is the super imprecise graph. Let me try and draw a straight line through it. Okay, so that's what our line of best fit would look like. Again, I did this on paper, so let me find what I got for delta y and delta x. Let's see. Okay, I got delta y is equal to 0.96 meters, and delta x is equal to 0.23 meters, or no, not meters, 0.23 seconds squared. So that makes delta y over delta x, or our slope, equal to 0.96 divided by 0.23, 4.729 meters per second squared. So if that is our slope, then we're asked to find gravity. We can see here that gravity is simply equal to 2 times our slope. So I'll just multiply that by 2. And we get gravity equals 9 point, I guess I will round it. No, actually, I'll do 9.46 meters per second squared. Alright, that's what we get. So that's kind of the first scenario. And now we have another student who's modeling this using a quadratic, or modeling the position over time using a quadratic, which is kind of what we're doing, but it's a little bit different because we kind of assume that initial velocity is 0. Anyway, they got some stuff going on here, but yeah. So we're given constants a, b, and c, which respectively represent coefficients of time squared, time, and time to the 0. And we have a function for y. So first we are asked to find a function for velocity. So let's do that. We know that velocity in a given direction is the derivative of position with respect to time. So we'll just take that derivative. We will power rule at squared to get 2at. And then constant multiple rule to get plus b. And then that constant disappears. We want to be really precise about this. You can plug in a and b. So 5.75 times 2. That's 11.5t, and then b is negative. Oh, I think I should say 0.524. Negative 0.524. And again, they define this where y is positive when you're going down. Okay, so we've got that. Now we're going to use their approximation to find their value for g. Well, we know that g so h equals 1/2 gt squared. H is effectively, if we kind of think of it as a continuing function, h is effectively our y position. So y equals 1/2 gt squared. And in their simulation, they've got some other variables too, but the only thing that is proportional to t squared, in other words, the only quadratic component, is a, and that is the one that is going to be proportional to g. So we can kind of see here, excluding the linear and the constant components, that if we match up at squared with 1/2 gt squared, then it's clear that a equals 1/2 g. In other words, g equals 2a, and that is 11.5 meters per second squared. So next, we're going to find the percent error of this value compared to the exception value for g, which is 9.81 meters per second squared. So for that, we'll just do kind of calculated value minus expected divided by the expected value times 100%. See what we get. And I'm getting 17.23% error. Okay, so finally, we're actually going to use this quadratic equation. We are given that the initial height is, or not the initial height actually, but kind of the final y, right? So like this position is 1.4 meters relative to the top. I'm just going to call this y actually, that makes more sense. The final y is 1.4 meters, and we're going to find the velocity right before the ball hits the ground. So what I'm going to do here is we're going to take this direct equation, plug in 1.4 meters, and see if we can find time, and then I'm going to use that time to find the velocity. So 1.4 equals 5.75 t squared minus 0.524 t. So we can say that that equals 0. Instead of solving the quadratic, I'm going to take the short route, optimize time, and I've actually already got it plugged in on my calculator here. I'm just going to graph it and find the y-intercept of this function. Let's see, can you see this? I don't know, but anyway, it looks like that. And then I'm just going to use the function to find the 0 with the given left bound and right bound. And I'm getting t equals let's call it 0.527. Actually, I'm going to go a bit more precise. 0.5269. Just increasing precision so that we make sure we're not rounding off once we calculate velocity based on time. Okay, so now we can use this, and we actually already have a velocity equation that we calculated in the first part of E. So we'll just plug that back in. Because now we know what A is, what time is, and what B is, because A and B are both given. I'll just plug that in. And that is going to run to 5.54 meters per second, which makes sense because we're going down, and we define down as positive y, so we're going to have a positive velocity. Okay, so just to recap, we started out to find how g was affected if our measured time ended up being greater than the actual time. Turned out that g would be less. Then we found the relationship between g, h, and t, and defined some axes Then we graphed it. We used the slope to find the gravitational constant. We looked at a quadratic model, found a function for velocity based on time, which ended up being 11.5t minus 0.524. Then we used that same model to find their estimated value for gravity, which was 11.5 meters per second squared. We found the percent error of that to the accepted value for gravity, which was 17.23%. And then finally, we took y equals 1.4 and found the associated final velocity that would solve the equation, and that was 5.54 meters per second. So yeah, that's about it. Thanks for watching.